The mass of a burning candle is monitored to determine the rate of combustion of paraffin, and they give us a balanced equation over here, or an acceptable balanced equation for the reaction. They give you the following data over there and expect you to draw a graph of y versus x. So that if you're going to do that, you're first going to label, going to give a heading, graph of mass of candle versus time. Then you're going to put the mass on the y-axis, and you're going to give it a unit grams, and you're going to put a time. As far as possible in physical science, do not eliminate the 0.00, and do not do the little jump over here so that you're in the 20s automatically. Physical science, we want to see what is happening relative to the 0.0. So you're now going to give even hops, 10, 20, 30, 40. And up here you're going to go 10, 20, 30. What that's going to mean is that your points are going to be pretty much in a small space. So there's 25,6, and then it's 25,1, and then it's 24,5. And what you land up with at the end is a straight line up over there. Very steady decline. It turns out that there are even changes over there, so it is a straight line graph. Calculate the average rate of consumption of paraffin in grams per minute for the time interval 12 to 24 minutes. So you're going to say from 12 to 24, change in y over change in x to get the rate, and it's going to be 23,4 minus 24,5 divided by 24 minus 12, and that's 0,09 grams per minute lost. Something along those lines. The next question was a very tough question, and you'll need to pay attention as to how we get that answer. So it's calculate the rate of carbon dioxide production in moles per minute for that same time interval. So what are we going to do about that? First thing we're going to do is we're going to say we want to know the rate of carbon dioxide production. And for that, so let's just make some space here. For that, I'm going to take a look at my balanced chemical equation. And I can see that I am producing carbon dioxide. That's what I'm looking for. What I've just measured is the mass of paraffin loss. Now we can look at it like a balanced chemical equation, and we can say the relationship between paraffin and carbon dioxide is a 2:56 relationship. So let's work out the number of moles in 0,09 grams of paraffin first. So number of moles is equal to mass over molar mass, which is 0,09, and the molar mass of paraffin is going to be equal to 28 times 12 plus 58, which turns out to be 394. That is then equal to 2,33 times 10 to the negative 4 moles, and that's of paraffin. Now I take that number of moles and I put it into a mole ratio. 2,33 times 10 to the negative 4 is 2. 2 is to 56, divide by 2, multiply by 56, and I get 6,52 times 10 to the negative 3 moles. The question they wanted is the rate of production in moles per minute. So this was the mass per minute that was used of paraffin, which means that this number of moles per minute was made of carbon dioxide. So if you want to write it out again, 6,52 times 10 to the negative 3 moles every minute. And that was a level 4 question. It was intended to be challenging, And it appears to have met that criteria, since very few people got anything right about it. Sodium bicarbonate is a key ingredient in antacid tablets. An antacid tablet is added to cold water to produce carbon dioxide. The gas is collected using the downward displacement of water, and they give me all of this information, and then they ask me once again to plot a graph. So once I've got my axes over there, again notice some things. Graph of y versus x, y-axis with a unit, x-axis with a unit. Label them both. Keep 0 in even spaces on the x-axis, even spaces on the y-axis, and you'll end up with something that looks a little bit like that. Not very specifically, maybe a little bit more of a jerky thing like that. But anyway, something like that. It's a bit of an S-bend troop, like that. Calculate the average rate of carbon dioxide gas for the time, for the following time. So it's first it's 0 to 10 seconds, and then it's 10 to 20 seconds. So we're going to work out both of those, and you're going to go change in y over change in x, so it's going to be 3 over 10, which is 0,3 milliliters per second, and then for 10 to 20 seconds it's 17, because it's 20 minus 3 divided by 10 seconds again, and I'll end up with 1,7 milliliters per second. Notice the unit is always just what's on the y-axis per what's on the x-axis. Suggest a reason why the rate of the reaction from 0 to 10 seconds is slower than the rate from 10 to 20. You could have given me two different answers. The first one is that the antacid tablet needs a little bit of time to break up, okay, which is a perfect, and then expose some surface area. The other is as the reaction starts, it starts to get hotter, and then it will speed up as it makes more heat into the reaction. So you could give two reasons why the rate increases. The rate of the reaction is not constant during the entire time from 10 to 40. Describe the changes in rate and explain the reason for that change. Well, initially we're going to get an increase, and then it starts to flatten out a bit because the reactant, or the antacid tablet, or the surface area of antacid tablet starts to decrease after the reaction has been proceeding for a while. Eventually the reaction actually stops at around about 40 seconds. And then 5, if the antacid tablet were added to hot water instead of cold water, what would happen to the rate of the reaction? Hot means it will increase. And why does it increase? In terms of collision theory, explain your observation, and most of you were really good about this. Heat is not kinetic energy. Some of you said heat is kinetic energy. Heat is directly proportional to kinetic energy. So you get more kinetic energy, and therefore more particles collide. So there's more movement, and therefore more collisions. And most of you did well on that. Now we look at this reaction. It says identify the catalyst. The catalyst has to be the same thing at the beginning and at the end. If you take a look at the beginning of step 1 and the end of step 3, there's only one substance that it could be, and that is water. Why? The catalyst remains unchanged from the beginning to the end of the reaction. And then you've got this Maxwell-Boltzmann distribution curve showing an uncatalyzed reaction. You need to understand what a Maxwell-Boltzmann is. It's telling you how many particles have got a certain amount of energy. So in this case, lots of particles have got that much energy. Fewer particles have got that much energy. Then this is called the activation energy, and only these particles over here have got enough energy to react. When it asks me to catalyze that, what do I do in a catalyzed reaction? Is I lower the activation energy. I don't change the heat of the particles, the kinetic energy of any particles. All I do is I make the activation energy lower. By doing that, I make more particles available to react. If we look at this reaction, identify two ways other than a catalyst to increase the rate. The first one is increase the temperature. The second one is increase the surface area of the zinc. You have to be specific. And the third one is increase the concentration of the hydrochloric acid. If you don't tell me what it's of, I'm not going to give you any marks, and nor is the matric examiner. Which reaction rate could be increased by an increase in surface area? Surface area means I must have a solid, so I go hunting for a solid, and this is the only one that's got solids in it, so B is your correct answer. And the next one, which of the following is not a measure of the rate of reaction? Rate of reaction is always something per unit time. Oh, goody, per unit time. Per second is a unit time. Per minute is a unit time. Per mole is not a unit time. So B is not a measure of the rate of a reaction. And lastly, this reaction over here, it tells you that it is an exothermic reaction. And I have got the effect of temperature and pressure on how much of this ammonia I have got. This is actually an equilibrium question and is more complicated, but at the level that you're at now with rates, if I've got a high pressure, I will get a lot of ammonia being formed. So either one where the high pressure gives me more. And if I've got a high temperature, I will have a lot of ammonia being formed. So as far as you're concerned, A is the best answer. However, this is really an equilibrium question, so I'm actually eliminating it, because what happens is that you land up with D being your correct answer due to equilibrium considerations, which we are going to come to later. So I'm going to eliminate that question from the paper.